So thank you everyone for being here. Welcome to the Mindlin lecture. So I would like first to start with that the ESS department gratefully acknowledge the generous support of Catherine and Lee Renleitner that are with us tonight. Yeah, thank you very much. Through the Mindlin Foundation, the foundation promotes excellence in education, engineering, and science by fostering collaboration between students and educators to address complex challenges and cultivate future leaders. It supports lecture series at universities, including the University of Washington, bringing distinguished experts, like tonight, to engage with students and faculty and broadly share ideas across disciplines. So it is a great honor and a privilege for us to welcome tonight to introduce our distinguished speaker, USC alumni, Dr. Christopher Glein. I'm going to run through my text. I was told that if it's too long, I need to switch on my French accent. So just to keep you entertained. But let's start. So Dr. Glein is an internationally recognized planetary scientist. And I want to say, like, he's probably one of the, like, in my opinion, one of the leaders in our field, highly respected, whose work addressed some of the most profound questions in modern science: how worlds form and evolve, and whether life might exist beyond Earth. He's a scientist at the Southwest Research Institute and arguably the world-leading authority on geochemistry of the solar system, big three icy ocean worlds: Enceladus, Europa, and Titan. Dr. Glein has developed many innovative methods that allow scientists to infer the chemical properties, internal processes, and evolutionary stories of these distant environments using spacecraft data. So over 19 years of experience building and applying chemical models, he has helped transform our understanding of the subsurface ocean, hidden beneath icy crust of the outer solar system and beyond, which we'll probably hear a little more tomorrow, beyond the solar system. His contribution has been central to interpreting data from the NASA Cassini mission, particularly measurements from the ion and neutral mass spectrometer, for which he served on the instrument team. Today, he continues to shape the future of planetary exploration as a co-investigator on the Europa Clipper mission, mass spectrometer for planetary exploration, MASSPEX, an instrument that will analyze material from Europa, tenuous atmosphere, and potential plumes in unprecedented details. He also recently served on the National Academy Decadal Survey for Planetary Science and Astrobiology, helping to define the priorities for our discipline for the future, for the coming decade. In addition to this, because it's not enough, you need to do a little more than that, Dr. Glein is also the principal investigator on the James Webb Space Telescope observing program focused on observing Enceladus, which, what I've heard, is quite an achievement as not being like an astronomer. So Dr. Glein earned his bachelor's degree of science at the University of Washington in 2006, and his PhD from the Arizona State University in 2012. We're therefore especially pleased to welcome him back to the Pacific Northwest tonight. So despite many years away, I've heard that he has remained a devoted fan of the Huskies, the Seahawks, and the Mariners. So this evening, he will present a lecture called Seafaring in Space, Personal Voyage to Enceladus. So please, ladies and gentlemen, join me in warmly welcoming Dr. Chris Glein.
Thank you. Do you hear me okay? All right. Well, if I get quiet, tell me to get louder. Thank you, Baptiste. It's a real treat for me to be speaking with you all tonight, and it's wonderful to see so many students in the audience. 20 years ago, I was in your shoes. I was a student at the University of Washington in this department. Yes, I know. It's been that long. I feel ancient. And this is just such a special place. And I'm so happy to be back in Johnson Hall once again. Before diving in, we have a lot of ground to cover. I'd first like to thank Baptiste for giving that fabulous introduction. Thank you, Baptiste. As well as Eric Steig and the rest of the ESS faculty for inviting me to give this year's Mindlin lecture. Thank you so much. And I'd also like to thank the Mindlin Foundation for their very generous support. Thank you very much. So I thought we would start with Seafaring in Space. And if you look closely at this title, it may ring a bell. This is based on a lecture I gave at the AGU meeting last December. It was called the Carl Sagan Lecture. So naturally, I'd like to start off by saying a few words about Carl and his influence on me. So I've become troubled in recent years. I work with quite a few students, and I've noticed that increasingly they don't recognize his face. Carl Sagan was one of my heroes. Sadly, he passed away. Now it's been nearly 30 years, and I never got the chance to meet him. But the beautiful thing is that he was still able to speak to me through his many recordings and writings, and I'd like to share a few with you all tonight. What did Carl Sagan do for us? He taught us a scientific worldview, how science is like a dance between two human qualities, wonder and skepticism. For my fellow old-timers, remember these strange black boxes. In episode 1 of Cosmos, Carl says, "The surface of the earth is the shore of the cosmic ocean. On the shore, we've learned most of what we know. Recently, we've waded a little way out, maybe ankle deep, and the water seems inviting." Carl also emphasized the vital role of skepticism in science. Without it, we risk seeing the world how we want it to be rather than the way it really is. Here he is again in one of my favorite books, The Demon-Haunted World. I have a foreboding of an America when awesome technological powers are in the hands of a very few, and no one representing the public interest can even grasp the issues, when the people have lost the ability to set their own agendas or knowledgeably question those in authority, when our critical faculties in decline, unable to distinguish between what feels good and what's true, we slide, almost without noticing, back into superstition and darkness. Clearly, we've dug ourselves quite the hole. But not all is lost, because the spirit of science is still with us. We just need to find a way to reawaken it in our society. That's easier said than done, right? But we've got to start somewhere, and there's no time like the present. So tonight, I invite you to join me in beginning a new chapter as we continue Carl's grand voyage of discovery in search of ourselves to renew a time of hope. One of our most profound questions is whether there is life beyond Earth. We desperately want to find one of these little guys. Desperately. Why do we search? There are many reasons, but one of the most compelling ones is to understand our place in the universe. This is deeply human. Throughout our history, there have been many stories about where we came from. In modern times, we have this narrative of cosmic evolution, which is simply a retelling of the natural history of the universe, from the Big Bang through galaxies, stars, and planetary systems. We've learned that the laws of physics are universal. So is chemistry. But biology, that remains a big question mark. There are other reasons to search. Many of us want to do something good for the world, contrary to what you might read on social media, and you really shouldn't read much, we're not in it for the money. We feel a higher calling. And this final reason, this really strikes close to my heart. There's just something utterly awesome about contemplating the big question. And this is the critical part, having the capability to go out there and start searching for some answers. So Alan Stern, he's a famous planetary scientist, he said this better than I can. We are living at the beginning of Star Trek. So what are we going to do? Well, from exploring the solar system and elsewhere, we've learned that there are some incredible opportunities out there. Don't you just love it when you hit jackpots? There's Mars, a former wet planet. Mars is a world that is brimming with wonders. We must go back to Mars, and we'll eventually send humans to explore the surface of Mars. There's Jupiter's moon, Europa, the OG ocean world. Europa is so important that we have a multi-billion-dollar spacecraft now headed to Europa, and it will arrive around the end of this decade. Europa is coming right up. There's Titan, Saturn's big moon. Titan is the only moon in the solar system that has a thick atmosphere. Some think that Titan is a world of two oceans, liquid hydrocarbon bodies on the surface. The surface is very cold, and liquid water, very deep underground. Titan is an object that is most worthy of our continued exploration. There's another moon of Saturn, Enceladus. I like to think of Enceladus as Saturn's snowy pearl to go along with the crown jewels of Saturn, its rings. We'll have a lot more to say about Enceladus throughout this talk. And finally, there's the exoplanets. These are planets that orbit other stars. We've discovered over 6,000 confirmed exoplanets. More are being discovered every day. Some of them orbit in just that right Goldilocks zone where liquid water could be stable on their surfaces. We might eventually find evidence of life on an exoplanet. So clearly, we're dealing with an abundance of riches. What are we going to do? Well, maybe viewing things as a free-for-all is not the most productive strategy in the search for life. It's a great game show, right? Instead, I would like to focus more narrowly and focus on oceans as being habitable environments. And I'm going to introduce this notion of Enceladus as a gateway to this new field that I call astro-oceanography. So this is the study of oceans in space. And Enceladus is a great gateway because its ocean is accessible, as we'll learn about soon. Now, I love analogies, so you have to bear with me. So here's a visualization of how I think about this notion. I present to you an animal theory of planetary science. This is a highly sophisticated theory with advanced mathematics behind it. By the way, it's not peer-reviewed. And the idea here is that Enceladus can serve as a model system for understanding planetary oceans, in a similar way as the mouse can serve as a convenient and useful laboratory model for understanding the physiology of mammals. If we can understand this model deeply, then we can use it to guide the exploration of other oceans in our solar system, like Europa and Titan. Eventually, the goal is to progress towards a more general theory and understanding of how planetary oceans work so we can gain insights into more exotic beasts that might be lurking beyond our cosmic neighborhood. So enough about all of that. Let's begin our voyage to Enceladus. The story of Enceladus starts with the birth of modern astronomy. Prior to the telescopic age, we only knew of 5 planets. The planet Saturn was the furthest planet you can see with the naked eye. That all dramatically changed in the year 1610 when Galileo famously observed the 4 big moons of Jupiter that we now know of as the Galilean satellites. Followed by that observation, we started to learn that not only Jupiter had moons, but Saturn had moons as well. We found Titan. Cassini-Huygens discovered Titan, 1655. Remember the name Huygens. Shortly thereafter, Giovanni Cassini, he's shown in the middle there next to Galileo, he discovered 4 other moons of Saturn, shown there, Iapetus, Rhea, Tethys, and Dione. But Enceladus eluded our views for another century. Enceladus, as you'll see in this image shown here, this is a high-powered telescopic image, you could see that Enceladus is a dot. That's why it was so hard to find. It wasn't until the late 1700s before Enceladus was discovered by this man, shown here on the far right, William Herschel. He's most famously known for discovering the planet Uranus. But Enceladus remained a dot for the next 200 years. That all changed in the 1980s. In the late 1970s, NASA devised the grand tour of the outer solar system. These are the twin Voyager spacecraft, Voyagers 1 and 2. And I'm going to show you various images throughout this talk of people who were highly influential or personally impacted me. And so shown on the far left, this is Ed Stone from JPL and Caltech. He was a Voyager project scientist for decades. He passed away recently. He's an incredibly important person for our understanding of the solar system. We flew Voyager 1 through the Saturn system in 1980, and it did a close flyby of Saturn's hazy moon Titan. And Carl Sagan was a big proponent of the importance of Titan. The following year, in 1981, we did a close flyby of Enceladus, and we first noticed that something was different. Enceladus was different from most other bodies in the solar system that are really heavily cratered, like our moon, for example. And the reason why a lot of these bodies are heavily cratered is because they've been geologically inactive for billions of years, so they've had a lot of time to accumulate craters over the eons. Enceladus looks like there was something that happened to erase those craters that we would expect to find. So there's evidence of some kind of geologically recent activity. But we didn't really quite know what that was. So that was the status as of 1981. Where was I? Well, I wasn't even here. That's before I was born. And this just gives you a sense of how I'm going to also chronicle my personal voyage throughout this talk. So my voyage has not even yet begun, but already I'm standing on the shoulders of these giants. Fast forward to the 90s, and these 3 men were known as the godfathers of this mission that became Cassini-Huygens. This is our first great expedition to the outer solar system of the 21st century. So this is Toby Owen from the US, Daniel Gautier from Paris Observatory in France, and Wing Ip, who was also part of the European Space Agency at that time. They conceived a flagship mission to go to Saturn, to follow up on all the questions we had after Voyager. And it was meant to be a close international partnership between the European Space Agency and NASA to foster scientific goodwill. And what a mission it was. Cassini has been called Battlestar Galactica. It's very expensive, but it was worth the money. It was well equipped with advanced instrumentation that is necessary to thoroughly investigate the Saturn system. That is, Saturn the planet, its deep interior, the magnificent rings, the moons, that magnetosphere. This is a system that we wish to interrogate. And it finally launched after over a decade of political turmoil, much like we might hear about today. it finally launched because of these kinds of proponents, and it was a spectacular nighttime launch in 1997. I was in high school at that time. So that's Glein's timeline. We finally reached Saturn in 2004. This is actually one of my favorite images. I don't personally study Saturn, but I can just appreciate the majesty of this image, showing Saturn and its rings in all their glory. At this time, I was actually a student at the University of Washington. And what I also show here is an image of me and my fellow traveler, because we seldom go on these long voyages alone. And you might also notice that I'm wearing husky purple in that photo. Cassini was a great mission. And we did a lot of fantastic things. This shows a timeline of the Cassini-Huygens missions. I mentioned we got there in 2004, and we spent the next 13 years studying the entire system. So in this image here, you can see we did a lot of flybys of Titan, because Titan is super important. But we also did a number of flybys of Enceladus, 23 in fact. And for those of you chuckling in the back of the room, this is again my voyage right here. And we're actually way off the screen now on my voyage. But it gives you a sense. If you're a student interested in planetary science, you got to think about the big picture and the long term. This field, especially exploring deep space, is not for the faint of heart. So let's talk about Enceladus a little bit. I want to give you two messages to remember about Enceladus. Enceladus is an icy moon, but it's also very, very small. Our moon is kind of small, but Enceladus is small on a whole nother level. This is an image to scale of Enceladus shown next to Great Britain. So you can really get a sense that it is a small world. I'm from Texas, so you could fit Enceladus. You could probably fit a few Enceladuses inside Texas. That's how small it is. If you were to take a car, drive around the equator, it would be about the same length of trip as from Chicago to Boston. That's how, you could knock that out in like a day, driving around the world on Enceladus. Another important piece of information is it orbits around Saturn. Saturn is around 1 billion miles from the sun. It's incredibly cold out there. The average surface temperature is similar to the temperature of liquid nitrogen. Or maybe even like a night in Seattle, as I learned as I stepped off the plane last night in shorts and a t-shirt coming from Texas. Well, I should mention one more thing. So there's actually a third thing you need to know. And this is particularly for Baptiste's sake. Enceladus is not to be confused with this tasty dish. Sorry, Baptiste. As I mentioned, Cassini made a number of revolutionary discoveries, but arguably the biggest discovery it made was the finding that Enceladus lacks all those craters because its geological activity isn't just recent, it's right now. We discovered that Enceladus is erupting as we speak. It's been erupting for at least the past 20 years. We discovered a gigantic plume of material that's erupting from the south pole of Enceladus. So you can see on the right-hand image here, that's a color-enhanced image showing how far the plume extends from the south pole. This is a cryovolcanic plume. So those of you who are familiar with volcanoes on the Earth are powered by silicate melting, where rocks melt. On Enceladus, instead of having rocks, it's cryo. So it's actually ices and water vapor that are erupting into space. And through the Cassini tour, we learned that this plume is supplied by over 101 jets and other curtain emissions that are lined all along the south pole of Enceladus, erupting materials into space. And then those jets eventually coalesce at higher altitudes to form this huge plume superstructure. You might wonder, well, where does this plume come from? We learned from detailed study with Cassini that the plume comes from a subsurface ocean of liquid water. So this is a cartoon representation of what we think is going on. I mentioned that you have all those jets, And those jets are erupting from these long cracks that line the surface of the south pole of Enceladus. And we learned that the plume is sourced by a deep plumbing system that goes down into the interior and eventually reaches a liquid water ocean on Enceladus. And you can see right up there at the very top, that's Cassini. We actually flew Cassini through the plume, and we sampled it. How'd the plume taste? It tasted salty. We learned that the plume tastes salty because we had the proper suite of instruments. I mentioned Cassini was well equipped, right? And we had an instrument known as a mass spectrometer. So what a mass spectrometer does is it can ingest particles that are in the space environment. And then what it can do is it can weigh those particles. So we can actually measure the masses of the different chemical constituents that are found in the plume. And when we measured those masses, we were astounded. Because the plume, those particles, very small icy grains, they contain salt, sodium chloride. So this image here, you can see I'm plotting the mass, and we're showing the amplitude of the detected signal. And you can see that there's a big peak right there for Na+. It's a chemical symbol for the sodium ion. So we found the salty, smoking gun of liquid water on Enceladus. We've learned much more since that first finding. We actually learned what the plume's chemical nature is by analyzing all the Cassini data. I just boiled it down to you right here. So we talked about the salt. What else is in that ocean is baking soda. So those of you who remember making volcanoes with your kids or your nephews or nieces, baking soda is one of the key ingredients. Another key ingredient, though, is washing soda. So that's the more alkaline version of baking soda. You can make washing soda if you put baking soda in your oven, and you can drive off some of the CO2 and water. So it's a more alkaline version. And the last major ingredient is ammonia. So we have experience with ammonia with Windex, right? Where you clean your windshield or your windows in your house. And we were able to take the chemical data from Cassini and then apply geochemical modeling. So this is one of the big things that I do is geochemical modeling to try to make sense of all these data, because it's just a bunch of data floating around, and then the modeling can provide some coherency. And I'm going to show you a little bit how this works. This might be a little bit of a scary diagram, so I'm going to walk you through it. So the image on the right shows a cartoon visualization of what we think is going on to convert the ocean water on Enceladus into the plume. And on the left-hand side, this is one of Cassini's most spectacular images. This is a close-in, high-resolution image of one of those massive cracks on the surface of Enceladus. So just to give you a sense, like the pixel scale of this is like 40 meters per pixel. So it's really zooming in quite closely. And what you're seeing on the right-hand side is this model of how we can imagine that the ocean water is vaporizing as it ascends up the crack, and then the vapor is gradually condensing to form solid ice particles. And through those processes, the relative abundances of different chemical constituents are changing. So we can use this chain of events that the model represents to solve what's known as like the inverse problem, where we take the observed composition and then we can infer what the original source composition was. And if you do that, you arrive at that table on the far right-hand side. There's a lot of numbers there, but what's really important to remember about this table, this is known as chemical speciation. And this is what oceanographers started to do in the 1960s when oceanography became a more quantitative science. And what I find really interesting about this exercise is we're now starting to do that for an extraterrestrial ocean. So this is where the birth of astro-oceanography is taking place. That's the geochemistry. I don't want to ignore any of you geophysicists in the audience. Here's what we've learned a little bit about the geophysics of Enceladus. So you might have heard the term ocean world, right? What does that mean, ocean world? Well, it means just what it sounds. We think that Enceladus has liquid water, and it's in an ocean layer. It's globally extensive. And this is the interior structure of Enceladus that we've been able to reconstruct through analyses of its gravitational field as well as its surface topography. And you can see it's interesting because it's complex. It's not just a uniform sphere. You can see the ice shell has variations as a function of latitude. It's kind of thick at the equator, and the equator is a relatively geologically inactive location. But then where the plumes are erupting, that's where the shell is thin. And we think the shell is only about 2 or 3 kilometers thick in the South Pole. So we think that's one of the primary reasons of how the how the ocean is able to erupt into outer space. And to give you a sense of scale here, for those of you who like to go diving, the Earth's oceans are on average 4 kilometers deep. The deepest trenches on the Earth, these are the deepest points in the seafloor, those are on the order of 10 to 11 kilometers in depth. The ocean on Enceladus, we think, averages about 40 kilometers in depth. So although it's a small moon, it hosts an incredibly deep ocean. Okay, so this actually gathered a lot of excitement when we realized that Enceladus had a liquid water ocean, because it started to open the door to thinking about whether there could be life on this small moon. Astrobiologists have a way of approaching this question of life. The first step we take is we ask ourselves, is that environment habitable? Which means life, an environment that could support life as we know it. That's kind of like our guiding mantra. There could be all sorts of strange forms of life out there. I'm a big fan of Star Trek. But we like to start with what we know because that helps to provide focus in our study. And the 3 ingredients that life on Earth needs is liquid water, a source of energy to power biochemical processes, and essential elements. So we think there's a deep ocean of liquid water, so we had a check mark there. The next question that emerges, could there be a source of energy that life could harness? And we set out to answer this question near the tail end of the Cassini mission. This was in late 2015. So I had just finished a postdoc, and I moved to my current position at the Southwest Research Institute. I moved there like October 7th or something like that. And then a week later, this flyby happened. So talk about, like getting ready to work. This is a very special flyby because this flyby allowed us to perform a deep dive through the plume and look for a very special molecule. And so this plot here shows the data that we collected. There's a couple of intriguing features I'd like to remark on. One, so you can see on the horizontal axis, seconds from closest approach, all of the action happens incredibly fast. Within 10 seconds, basically, is when the data are collected. And that's because the Cassini spacecraft is screaming past Enceladus at roughly 8 kilometers per second, its velocity. And it ends up getting 49 kilometers from the surface of Enceladus at its closest approach. So it's a deep plume fly-through. And then what we detected, what the symbols represent, is they represent what the instrument detected. This is known as the ion and neutral mass spectrometer. And it was able to detect gases that flew into the instrument inlet when we flew through the plume. And you could see various colors of symbols. So the green symbols shown at the bottom, those are the instrument background at this massa 2. So all sorts of instruments have some kind of noise level and background. And you got to be really careful that you properly characterize that before you start to form interpretations of the data. So we performed a really intense campaign in testing the engineering model at SWRI, so that's Southwest Research, to define that instrument background there. Once we did that, then we could compare that background to some of the detected signal. And what we found was, you could see in blue and purple in that plot, we detected counts in the instruments. That's data. That's signal that we detected that were well above the background. And from that detection, we concluded that there is a mass 2 species in the plume, and that mass 2 species is molecular hydrogen, H2, and it's present at about 1% relative abundance in the plume. H2. So if you're an astronomer, I love to pick on astronomers. If you're an astronomer, you might be quietly thinking, so what? Hydrogen is everywhere, and you would be correct. So on the far left-hand side there, those are known as the solar abundances. Those are the chemical elements that are most abundant in the sun and elsewhere in the solar system. Number 1 on that list is hydrogen. On the right-hand side there is a beautiful, it's a kind of a psychedelic image of Jupiter that was acquired by the Juno orbiter over the past decade. Jupiter is a huge gas giant. And what is its atmosphere made of? Hydrogen. But H2 is actually rare on small solid bodies. So if you look in the Earth's atmosphere, our atmosphere is not like Jupiter's. Our atmosphere has less than 1 parts per million of hydrogen. And one of the reasons for that is hydrogen is a very low mass molecule. It's light. Solid planets are generally lightweights. They don't have much gravity. So hydrogen is very prone to escaping from their surfaces and atmospheres and being lost into outer space. But there are certain environments on these special worlds where hydrogen is found. And it's found because it's constantly produced. And the most famous of these environments are hydrothermal vents at the bottom of the ocean, where geological processes allow water to access hot rocks. And when you have that interaction, geochemistry happens. Oh, I should mention, so right there in the middle, that was one of my postdoc advisors named Barbara Sherwood Lawler. She's the queen of hydrogen. She knows everything about hydrogen. And she really imparted the wisdom to me that rocks are an important part of the puzzle. Another person who is highly influential in my thinking is shown on this slide here, John Barrows. He's a professor. I think he's retired now, but he was a professor in oceanography. And he was incredibly influential in opening my eyes to thinking about this special type of water-rock interaction, which is known as serpentinization. It's a mouthful, but it involves a special type of rock that's rich in magnesium and iron, and it provides a way of supercharging hydrogen generation through geochemistry. So here's the image that we landed on. We think this is the story that hydrogen tells us about Enceladus. So just to give you a little bit of context, what we see is at the surface. So we detect a plume, we detect molecules in the plume. And then those molecules, through geochemistry, we can open a window into the interior. And that's where all the action is, all the excitement is what's going on in the interior. And from these measurements, we've been able to piece together that there is a deep ocean of liquid water. And not only that, but there's actually, we think, evidence that the water in that ocean is circulating through rocks at the seafloor. There's heating processes which are allowing hydrogen to be produced from the water. This got a lot of people excited. So while I mentioned the Voyagers were being developed in the late 1970s, around that same time, a revolution was happening not in space, but actually in Earth. People had built submarines, and they were exploring the depths of our oceans, and we made the remarkable discovery that hydrothermal vents exist at the bottom of our oceans, and these vents host life. Prior to that time, the life that we mostly knew was the life that we could find that was really accessible on the continents, for example, or in close to the continents or at the surface of the ocean. But we found the discoverers called these like alien ecosystems because it almost looked like another planet down there on the seafloor. It's in total darkness, but yet when you go near these hydrothermal vents, there's actually ecosystems there and life that's thriving. How does it thrive? Well, there's a food chain there. And that food chain, at the base of the food chain, is not plants like we find here on the surface of the earth, but it's actually microbes that feed off of chemicals that come from the deeper planet. And this got a lot of people excited for Enceladus and other ocean worlds because a key reaction that these microbes feed off of is known as methanogenesis. So hopefully I don't show you too much chemistry in today's talk. This is just the chemical equation for this reaction. It's called methanogenesis because methane is generated. So what the microbes do is they take CO2 in the fluid and then they combine it with molecular hydrogen, and when they perform that reaction, they make methane. And one of the key benefits of producing methane is they also get a little jolt of energy from performing that reaction. So it's great. And here's something we could do that we couldn't do prior to Cassini. This shows a diagram. It's a thermodynamic diagram. And what I'm pointing out here is what's known as the affinity. That's how much Gibbs free energy is available in the environment or from a reaction. So Gibbs free energy, that's delta G, right? Remember in general chemistry? Delta G is extremely important because if you're a microbe and you want to feed off of chemicals, the reaction needs to provide enough free energy for you to do something useful. Equilibrium is bad for all of us, including the microbes. That's death. What we wanted to ask ourselves is how much chemical energy, if there is any on Enceladus, might the observations reveal? Here's how much microbes need on the Earth. They need roughly 10 to 20 kilojoules per mole to keep things going. And what we did is we combined all of the Cassini data. So I mentioned earlier the alkaline ocean. And then we used our new measurement of hydrogen in the plume. And then we could finally complete this puzzle. So you could see, okay, here's the hydrogen measurement. There's the pH measurements. And then the spot that's shaded in blue there, that's the spot of consistency with all the data that we acquired from Cassini. And what you can see by just comparing that shaded blue region to the microbes' energy need is that the blue is above the green lines, right? So what that allowed us to conclude, if you think like an economist, the energy supply was greater than the demand. And so we concluded that Enceladus is energetically habitable. There's enough energy available that could support microbial life. I spent a long time talking to a reporter about this. I kept saying 10 to 20 kilojoules, and she kept, I don't really know what you're talking about. And then somehow I had this idea of, okay, actually, the amount of energy that Enceladus is releasing is equivalent to 300 cheese pizzas per hour. And then, it's like the light bulb went off. Okay, yeah, that's a lot of food. That seems like a great place to live. So I would agree. All right, so around 2020, this is our view of Enceladus habitability. We had found the water. We had found the energy. The last question was about elements. And this is work that I started with one of my friends, Jiwa Hao, when he was a postdoc at Rutgers University. We wanted to ask this very important question: is there P in Enceladus' ocean? And it's extremely important for habitability because phosphorus is a critical building block of life. Your bones are made of phosphate-bearing minerals. More significantly, your DNA contains phosphorus. ATP, this is adenosine triphosphate. This is the way that your cells are able to direct the usage of energy to perform useful functions. Without phosphorus, that molecule cannot function. So it's extremely important. It's a critical ingredient of life, and yet it's rare at the surface of Earth. A lot of people assumed it's rare everywhere. So we decided to look into this, and we performed geochemical modeling. So this shows a couple of diagrams where we try to predict the phosphate abundance as a function of all the data we had available from Cassini. Things like the pH of the ocean and other aspects of the aqueous geochemistry. What we found, you can see, so our predictions are these gray bands. And then this other dark green rectangle, that's Earth's seawater. We know that seawater is habitable, and yet you could see for large swaths of Enceladus' ocean conditions, we would predict there to be much more phosphorus than we find in Earth's oceans. At the time, this is really surprising because people were convinced, based on our experience on Earth, that phosphorus has to be rare in natural water environments. This got the attention of one of my friends, this guy here, Frank Postber. He's a brilliant scientist. He's somebody who can work with the Cassini data in the E-ring of Saturn. The E-ring is shown right here. So the big bright ring is known as the B-ring of Saturn. The E-ring is the Enceladus ring. This is a ring that's formed by Enceladus when the ice volcano is erupting so violently into space that some of those particles reach velocities that are greater than the escape velocity, and they leave Enceladus and go into orbit around Saturn. The beauty of the E-ring is a collection of samples from Enceladus' ocean. So we can sample the ocean by sampling the E-ring. That's what Frank did. Here's what he found. He found a new population of icy grains that are rich in sodium phosphate-bearing minerals. This was shocking at the time. What he found is that phosphorus is at least 2 orders of magnitude more abundant in these ocean samples from Enceladus than in Earth's seawater. This is a phosphorus-rich system, kind of like the model suggested. And the way this works, it's beautiful chemistry. I love chemistry. So the way it works is this an example of something known as Le Chatelier's principle. Oh, Baptiste, one of your countrymen. And every person in freshman chemistry learns this principle. And what it basically tells you is that if the chemical system is perturbed in some way, the system tends to respond in a way to relax that perturbation. The key perturbation on Enceladus is the high abundance of carbonate, the baking soda in the ocean. And what that basically does is it sets off a series of dominoes through Le Chatelier's principle. You can kind of follow it here. So you have lots of carbonates. That propagates through solubility equilibria with calcium carbonate minerals at the seafloor. Because there's lots of carbonate, there must be low amounts of calcium to compensate. If there's low amounts of calcium that are in equilibrium with calcium phosphates, those minerals must respond to low calcium with high phosphorus. So it's a beautiful example of freshman chemistry. that predicted a phosphate-rich ocean on Enceladus. And one of the pioneers of this idea was this man right here, David Catling. He's not in tonight's audience, so I can actually say some nice things about him. This man changed my life. I was an undergraduate at the University of Washington, probably more aimless than anyone else in this room. And I got excited about astrobiology. I went to his office one day. I asked him if I could do research. I don't know why he said yes, but he did. And that set the course of my career. He's one of the most brilliant, generous, creative scientists I've ever met. He's also kind of funny, too, if you know him, like in that scientist kind of way. It's great. And what he pointed out is you can actually find Enceladus on Earth. So it's not seawater. We actually can find these locations, soda lakes, that are on the continents in arid regions of the Earth. And these environments have the same type of geochemistry that this icy moon has, where you have lots of carbonates dissolved in the water. And it turns out, if you look at the data, where you have lots of carbonate, you have lots of phosphorus. Follows a beautiful trend. Here's Enceladus compared with the soda lakes that we know. So here's today's view of Enceladus habitability. We've almost found all the ingredients that life would need. The only thing that we're not quite sure about yet is sulfur. But that's a remarkably fine achievement by Cassini. This mission was not designed to sample the ocean of an icy moon. Yet we had the foresight to include those powerful instrumentation that could allow us to explore this question. This is a good summary of what we discovered. This is from The Onion. One of Saturn's moons discovered to have all the ingredients for mouth-watering enchiladas on Enceladus. So the next question, this is really the billion-dollar question, is Enceladus inhabited? We don't know. That's a question for the students in this room. It will be your generation who might answer this question. I better speed up because we're kind of running low on time. Why we want to go back and study habitable environments is to answer, one of the reasons, this is my reason, is I want to answer this question. Is the origin of life hard? We don't know the answer to that question. We have one sample of life. So if you do statistics, you can't really work out the solution to this problem. This field started with a bang in the 1950s, right around the time the double helix was discovered. This man, shown here, named Stanley Miller, he performed the Miller-Urey experiment. He sparked a primordial mixture of gases in the presence of liquid water and made amino acids. There was tremendous excitement that we were on the precipice of answering the origin of life. But life threw a curveball. It turned out that this is a harder problem than it first appeared. And progress has slowed over, especially the past 20-some years. So my conclusion is that we need new clues. And one of the best ways of getting clues is to explore. So you're probably familiar with the story of Charles Darwin. He didn't just sit in a room at a blackboard and come up with a theory of evolution. He went and he traveled. He went on his voyage. He gathered the evidence, and the evidence led him to the theory of evolution through natural selection. We need that moment. So here's just an example of the thinking. You know, if according to some physicists, organic chemistry and water, if you just spark it with some energy, life inevitably arises, then an environment like Enceladus should be inhabited. But if more specific requirements are needed, then a lack of life on Enceladus might provide some new clues and clarity to what those critical conditions might be. So a negative result, I'd love a positive result, but a negative result can be powerful scientifically. And we need to go search. So the scientific community recognizes this. Every 10 years, the National Academy puts out this report of what NASA should do. It's called the Decadal Survey. And in the last report that was released in 2022, I've done you guys a favor and highlighted that they recommended that a new mission to Enceladus be started, known as the Orbi Lander. So this would be the grand successor to Cassini-Huygens that's meant to search for evidence of life on Enceladus. Our European friends have taken notice, and they've already begun the next chapter. They have started a mission they call L4. So this is the fourth large class mission of the European Space Agency, and they are planning to develop a mission that would be both an orbiter and a lander. They're planning to officially adopt the mission around 2034, launch it about 10 years later, and reach Saturn in the 2050s. So eat your vegetables. This mission will look for signs of life, biosignatures, these telltale molecules that might indicate the presence of biology. It will look for further evidence of habitable conditions. It will provide the critical context of how habitability is created through geological processes. It will provide a system-level perspective of Enceladus. Here's what it's planned to look like. This is pretty cool, to be honest. So the mission is envisioned, I mentioned, as an orbiter and lander. What they're planning to do is they're going to send the spacecraft to first do a tour of Saturn's moons. So this will be Titan and a bunch of these other small moons, including Enceladus. And they'll scout out a safe place to land near the South Pole. And then in 2058, they're going to send this lander to the surface of Enceladus. And the surface is great because that's where the plume basically creates snow out of seawater. And so the snow is coating the surface. You can just take a big scoop of that stuff and look for organic molecules in that snowfall. But we should remember what Carl Sagan taught us many years ago. Extraordinary claims require extraordinary evidence. Okay, so I think Baptiste is going to kick me out soon, so I'm going to try to wrap things up pretty quickly. Right, so many of us, although I'm pretty patient, I'm not infinitely patient. So what can we do in the near term? Our current mission to Enceladus is this mission, the James Webb Space Telescope. It's been operational since 2022. It's revolutionizing all areas of astronomy, and we've used it to look at Enceladus and other icy moons. This shows some of the data, the first data that were collected. So we've observed both the surface chemistry of Enceladus, and then what's particularly exciting, shown in this bottom panel, we've actually detected water molecules that are being released from Enceladus' surface. So what is this? That's the plume, folks, right? JWST can see the plume. Pretty incredible. JWST is positioned close to the Earth's orbit. Saturn is almost 1 billion miles away, and this telescope can see the plume. It took Cassini, that was in orbit at Saturn, to discover the plume, and we can actually monitor it with this telescope. And we gained a fuller appreciation. The plume is massive. Enceladus is a pixel in this image, and you could see the plume extending all the way down on this image. So the plume is taking over Saturn's space environment and polluting it with all sorts of wonderful molecules that we're able to detect. And Baptiste mentioned I'm a PI of a program. We observed Enceladus again a year later, and we have even better data that I'll be able to share hopefully soon. All right, so we're down to the final stretch of the talk here. So we've had a lot of fun, I hope. But I'd like to conclude tonight's lecture on a more serious note. We began by hearing from the legendary Carl Sagan. We conclude with two other luminaries of the 20th century, Arthur C. Clarke and H.G. Wells. Clarke was most famous for writing 2001, A Space Odyssey. And Wells, he wrote The War of the Worlds. Here they tell us there is no way back into the past. The choice is the universe or nothing. With this in mind, I'd like to share a few personal reflections. In only 400 years, we've come so far through the methods of science. We've left the sunny shores of Earth and reached the shore of a distant ocean world. I believe we'll see many more. Our accomplishments, they should hearten us. Our ancestors, they did well. They made posterity proud. The progress we made gives us resolve to continue pushing forward. There's always progress to be made. In The Demon-Haunted World, one of my favorite books I mentioned earlier, Carl Sagan presented science as a candle in the dark that can be used to ward off our tendency of self-deception. Our predecessors, they were imperfect, but they did well in keeping and caring for the flame of science. Now it's our turn. We face many challenges, right? But our biggest responsibility is to educate the next generation. That's why I'm so happy to be here tonight. We need to teach them scientific thinking. We need to teach them how we know, not just what we know. Never stop dreaming, exploring, and questioning. Aim further than the last generation, even when it gets hard, especially when it gets hard. It's hard right now, right? We've got work to do. Leave a mark on this world or on another one that will make posterity proud. Aim for excellence in whatever you choose to do. And think about the long term. I mentioned space exploration is decades. We scientists, we're a proud bunch, right? And our reputations are our most valuable currency. Use it wisely. And finally, the pale blue dot. Over a generation ago, Carl Sagan introduced us to the preciousness, fragility, and isolation of our home world. However, with the passing of time, there's now a new generation that can benefit from the cosmic perspective. That's many of you. This image was taken by the Cassini spacecraft in 2013. It was organized by Carolyn Porco and the imaging science team. They called it the day the Earth smiled. On that day, people from all around the world, they looked up at the sky, they waved, and they smiled as their photograph was taken. This image, this is a powerful reminder that we are adrift in a vast ocean of the cosmos. If there's anyone out there, they will be much too far away to save us from ourselves. Our best chance for long-term survival is to remember that we are one world, and we need to look out for one another and for the rest of the biosphere. Our long voyage in search of life elsewhere gives us a new perspective to value and cherish the life that we have. Thank you.
Thank you so much, Chris. That's fantastic.
we have time for question. So is there any question? I would like to encourage students to go first if they feel like it, to raise their hand and ask some questions.
So how do you plan to find sulfur?
Well, the easiest way to do that is to bring a sensitive mass spectrometer back to Enceladus and to look for H2S, hydrogen sulfide. Another way you can do it is, this is a little more technical. One of the mass spectrometer that detected salt on Enceladus, it's a dust mass spectrometer, and it was designed to detect cations, which are positively charged species, like sodium, right? We now have the technology to make mass spectrometers that can detect both cations and anions. And anions would be important to look for a species called sulfate, which is a major source of sulfur for microbes on the Earth.
I don't know much about the processes of space science and whatnot. I'm still learning. But so you said 2050 about is when estimated. So my trajectory would be the equivalent of your trajectory now. So you'd send out this mass spectrometer. How would we get that data back to us? Do we have to wait another 20 years for it to come back, and then we gather the information, or is it how does it get back to us?
Oh, the data actually come back at the speed of light. So we use radio communications from an antenna on the spacecraft, and then it's received by what's known as the Deep Space Network, which is a collection of big dishes that receive telecommunications from spacecraft in deep space. So that's how we get the data back.
Is there a lot of noise when it's coming back, or do you have to discern between what is the information being sent and what's interrupting those waves?
It's not really my area of expertise, but I'm not aware of any noise that's introduced from transmitting data. I guess if you were transmitting over very long distances, it might be different, but for distances like Mars and Jupiter or Saturn, we haven't had issues. The bigger issue actually is that with these advanced instruments, we start to collect gigabits of information, and that presents a challenge for transmitting all that information back. So you might have heard I mentioned Alan Stern. He's the PI of the New Horizons mission to Pluto, and that mission had to have staggered data sending because there just wasn't enough bandwidth to send all that data back immediately. So you might remember in 2015, when we did the close flyby of Pluto, there were only a few images that were initially transmitted, kind of the juiciest tidbits before the whole data transmission was finished months later.
I have some questions about the rock-water interactions and hydrothermal vents. Given Enceladus' size, what would be leading to the heat that's needed to catalyze those reactions?
It's a great question. It's still actually a work in progress. We think the most likely candidate is this process known as tidal heating, where an object, so if you're a moon, let's say, in orbit around a giant planet, if the moon doesn't have a perfectly circular orbit, you can have gravitational tugs that defer at different points of its orbit, and that can lead to this process of deforming the interior, and that leads to this process of, we call it dissipation, which is basically friction between grains. And that friction, just like if you rub your hands together, that friction can generate a lot of heat. And probably the most spectacular manifestation of tidal heating is Jupiter's moon Io, which is the most volcanically active body in the solar system, and it is sustained by tidal heating. Enceladus is weaker tidal heating, and instead of seeing the spectacular fire fountains like on Io, we see the spectacular ice fountain at the plume.
Hello. I was mostly wondering when it comes to the lander itself. So Enceladus has a variety of different formations on its surface. One very notably being the geysers. I was wondering where the lander was going to land in relation to those. Is it going to try and land close by or in the highlands?
It's a challenge. So when you do a space mission, you got to weigh all these different trades. From a science point of view, I would like to tell the engineers, let's land as close to one of those vents as possible to get the freshest samples of the ocean, right? But that entails risk because that terrain near those vents is not well mapped out. So there's a risk, what if the spacecraft tips over or encounters some kind of very rough terrain or boulders that would compromise the mission? So I think why we consider missions that are known as orbilanders, which would first orbit and then land, is because when you first orbit, you can do all this mapping, right, to really understand the topography and all the risk. And then once you have those data, you can make a decision. Do I want to land someplace in the South Polar region where the science is really compelling, or do I want to try to land, let's say, closer to the equator, where I might get some distal plume fallout, where I could still gain really useful science, but then I also decrease my risk of mission failure. So that's kind of the logic that goes into those decisions. And to be honest, it's kind of like an ongoing dialogue between scientists and engineers to try to make the most informed decision.
Okay, thank you.
So you mentioned that Enceladus, in your view, is sort of the gateway to astro-oceanography. I'm curious, why for you it's Enceladus and not Europa, and sort of what those biggest differences are that you see between the two of those really similar water worlds.
Yeah, it's a great question. So I always get baited by reporters into trying to tell them what's your favorite moon, and I don't actually have a favorite moon because I studied Enceladus with Cassini. And I'm now on the Europa Clipper mission. I love Europa. I think it's a really cool moon. The reason why I consider Enceladus the gateway is because it's easy. So we've documented the plume erupting. We have strong evidence that comes from the ocean. So we're able to do detailed compositional analysis of those ocean samples. Europa is still very mysterious. People have suggested that plumes might be found, and then they're not confirmed, and it's all very confusing right now what Europa is telling us. So that's why I'm presenting Enceladus as a gateway, because it's the easy step. I think we first want to try to approach the easy step before we tackle the harder problem, which is Europa.
So if it's a small planet and it's, there's the icy, and then there's water, and then there's a little core, and the water is going out through the plume, is it eventually going to shrink even to just the tiny core?
It could, yeah. I did that calculation a long time ago. So if you were to extrapolate the current loss rate is about 200 to 300 kilograms per second. If you were to extrapolate that, you could remove a decent chunk of the total mass of Enceladus through solar system history. And so that might have interesting implications for the history of the Saturn environment. One thing that's interesting, I didn't mention it too much, is I mentioned that Enceladus pollutes the entire system. The material from Enceladus actually coats some of the other inner moons of Saturn with fresher material. And in fact, some of that, the plume material, actually is delivered all the way out to Titan. And Titan's atmosphere contains carbon monoxide, CO, which is not expected in the methane-rich environment unless you have a steady delivery of oxygen atoms to Titan. So Enceladus is actually able to modify the compositions throughout the Saturn environment. So it's a small moon with a big influence.
So obviously in Orbilander, you need to be like careful about how much weight it has and how like where it'd be landing. So if it's going to be landing like directly where the snow is falling, then how is it going to be getting power to send all those messages back and like keep doing experiments?
So you have a couple of choices. First, you cannot do solar power. Like, see, you've probably seen many of the Mars landers have solar power. At Saturn, the sunlight is just too faint to have any reasonable solar power, especially on a lander. So you're left with two options. You can either have batteries. Batteries are fairly easy to put on the spacecraft, but the disadvantage of batteries are they deplete quickly. So you might have like 2 weeks to a month of operations if you use batteries. So that's going to limit how many samples you can analyze, or if you wish to explore that nearby environment, you're going to be limited in how far you can go on battery power. Another option is nuclear power. You can have a radioisotope source. That's really nice because you can have long duration missions. There's two problems with nuclear power, though. One problem is a political problem. So you need to have a steady and reliable source of nuclear power sources generated. So you got to plan ahead to make the nuclear power source available. It's called they're clads. You have to have enough of them. And the other problem with nuclear power is it introduces this issue with what's known as planetary protection, where so from War of the Worlds, we don't want the aliens invading us. Well, they don't want us invading them as well. So if there's microbes in Enceladus' ocean, we don't want to inadvertently introduce Earth life that might be hitchhiking on the spacecraft. And so that's where nuclear power is a potential risk, is because it's such a long-lived power source that even when the mission is done, that nuclear power source is still live. And that might lead to some probability that would be deemed non-negligible for introducing microbes into the ocean. And that would compromise our entire scientific program to search for life on an icy moon. So you got to weigh these factors, and a solution hasn't been found yet, and we're still working on these issues.
So I'm just wondering, like, in general, how can you compare like hydrothermal vents in the Earth system to like this like icy kind of moon situation? Because like I understand like it's not, you can't do photosynthesis, but for me it feels like that's like the only similarity that there is between those two environments. So like could you expand on it a little bit, please?
So in planetary science, we're data limited, and what you got to do is you got to kind of like connect the dots, and what that means is you got to use insights from a variety of systems to try to paint that full image of what's happening. So I mentioned like soda lakes. That's one piece of the puzzle. We think hydrothermal systems are another piece, and the general features and insights that we've gained from studying hydrothermal systems on Earth can help us to understand these environments beyond Earth. But the details will probably differ, right? Because on Earth, a big contributor to hydrothermal activity is plate tectonics, and the heat engine of the Earth. On this icy moon, you're not going to have that same kind of geophysical context. It's going to be, because this tidal heating context is much different from what we're familiar with. So in that sense, you can't directly take the Earth analogy and just plop it onto Enceladus. But we're hoping that the general concepts of how hydrothermal systems can create chemical disequilibrium, and then that can be used to support habitability. We think that applies.
Okay. So, I mean, like, out of all those planets and moons and things like that could have life, which one do you think is the most likely and all that?
Well, I have a 3-word answer for that. I don't know, actually. That's why I think it's beautiful that we can be explorers. We don't have to have any kind of, we don't have to make our bet ahead of time. So I showed you the slot machines. We don't have to, it's not like going to Las Vegas where we have to make a bet ahead of time and say, okay, the environment needs to be this way. We through exploring, it's just pure exploration. We're learning about how environments work. Some of those conditions may be favorable for life. Some may not be. As a planetary scientist, I'm okay with the second option because we're going to learn more about how the solar system works, how oceans work on other planets, and we're going to gain a broader scientific perspective. So that's the view I bring when we're exploring these other places, is just be prepared to take the data as they come.
One last question.
So you compare the geochemistry of Enceladus's ocean to these soda lakes that we find on Earth. Can you talk a bit more about like what kind of ecosystems we find in those soda lakes? Are they rich ones? Are they ones where we would expect to find a lot of interesting things happening? Are they, yeah.
Yeah, so soda lakes seem to be very useful analogs for the geochemistry of this kind of icy world ocean. The biological context is a little bit, it's not quite, you can't really directly apply that because a soda lake, well, there's a couple of differences, right? A soda lake is on the surface of the Earth, so it's exposed to sunlight. And so that means that photosynthesis is actually a really important source of biological activity in soda lakes. And that doesn't apply on Enceladus. Another difference is, so soda lakes are on the surface of the Earth, so they're in contact with Earth's O2-rich atmosphere. And that's different, and O2, of course, is produced by photosynthesis. So that's another aspect where the analogy doesn't directly apply. And so we kind of got to marry different concepts where the soda lake gives us insights about one aspect of Enceladus, but then other environments can better represent other aspects, like the ocean being anoxic and hydrogen rich. And that's where, for example, I mentioned Lost City, or maybe I forgot to mention, but these hydrothermal systems at the seafloor where they can provide other clues to what's happening.
Okay, is there any other question from, not necessarily just from students? No? Okay. So with that, I would like to thank again Chris for this fabulous talk. And again, we want to thank you, Lee and Catherine from the Mindlin Foundation, to allowing us to have this event tonight. Thank you so much. So tomorrow, Chris will give another talk, more on exoplanet, as far as I understand it.
Yes, yes.
So please join us for that as well, and have a good evening. Thank you so much.
Thank you.